Hi, hello. Rachel, Irish, good afternoon. Good afternoon, everyone. Hope you're ready for our next session today, March 30, 2020. Today we'll discuss the optional treatment of thermodynamics, the molar heat capacity. So the molar heat capacity C is defined as the heat per unit mole per degree Celsius or per Celsius degree. Specific heat capacity. So remember that the definition of specific heat capacity as the heat per unit mass required to change the temperature. So this is given in this formula. C equals Q divided by M delta T. So C is the specific heat capacity, Q is the heat, M is the mass, and delta T is the change of temperature. So for example, copper has a specific heat capacity of 390 joules per kilograms Kelvin. Then we have what we call molar specific heat capacity. So in this case, the mole is a better reference for gases than is the kilogram. Thus, the molar specific heat capacity is defined by this formula. C, or the molar specific heat capacity, equals Q divided by N delta T. So again, C is the molar specific heat capacity, Q is the heat, N is the number of moles, and delta T is the change of temperature. So for example, a constant volume of oxygen requires 21.1 joules to raise the temperature of 1 mole by 1 Kelvin degree. specific heat capacity, constant volume. So how much heat is required to raise the temperature of 2 moles of oxygen, 2 parts of oxygen, from 0 degrees Celsius to 100 degrees Celsius? So from the formula, Q equals N CV delta T. So let's have one very good example here. So specific heat capacity, constant volume. Okay, so here's the problem. How much heat is required to raise the temperature of 2 moles of oxygen? So we have O2, means the 2 parts of oxygen, from 0 degrees Celsius to 100 degree Celsius. So this problem can be solved using the formula we have given a while ago, and we just manipulate this formula. So we have Q equals N delta C sub V delta T. So that formula is taken from C equals Q divided by N delta T. Right? So cross multiplying, or multiplied both sides by N delta T. So we have C multiplied by N delta T equals Q over N delta T, multiply this by N delta T. So we have delta T here, N delta T, and N delta T here. So we have Q equal to N delta T C. Right? Or Q is equal to N delta T C. Or we can rewrite this as Q equals N times C delta T. And we're talking of constant volume, so therefore our C, specific heat, constant volume, delta T. So this is the formula that is specified in that slide. So substituting, we have N equal to 2 moles, and the specific heat capacity of oxygen is 21.1 joules per mole degree Kelvin, and delta T is 373 minus 273 degree Kelvin. So therefore we have Q is equal to positive 4,220 joules. So that's the heat required to raise the temperature of 2 moles of 2 parts of oxygen from 0 degrees Celsius to 100 degree Celsius. Alright, so let's continue. Specific heat capacity with constant volume. So since the volume has not changed, no work is done. So the entire 4,220 joules goes to increase the internal energy delta U. Okay? So therefore, delta Q, or the change of heat, equal to the change of internal energy, or delta U, equal to N times the specific heat capacity with a constant volume times delta T equal to 4,220 joules. So delta U therefore is equal to N times C sub V times delta T. Thus, delta U is determined by the change of temperature and the specific heat at constant volume. Okay? Now let's continue with specific heat capacity in a constant pressure. Alright, we have just seen that 4,220 joules of heat were needed at constant volume. Suppose we want to also do 1,000 joules of work at a constant pressure. So we have from the relationship that delta Q equals delta U plus delta W, or the change of heat is just equivalent to the change of the internal energy plus the change of work. So substituting, we have delta Q equals 4,220 joules plus 1,000 joules. So we have delta Q, or the change of heat, equals 5,220 joules. Okay, so this change of internal energy, that is 4,220 is just the same. So we can say that Cp is greater than Cv, or the heat capacity for with a constant pressure is greater than the specific heat capacity in a constant volume. Okay? So heat to raise temperature of an ideal gas, delta U, is the same for any process. So therefore, delta U equal to N delta Cv delta T. So for constant pressure, we have delta Q equals delta U plus delta W. Or since delta Q equal to N Cp delta T, and delta U is in Cv delta T, plus the delta W is equal to P delta V, as discussed in our previous lecture. So here we can see that the heat capacity with a constant pressure is greater than with the heat capacity in a constant volume. Alright, so that's the relationship, class, that we need to understand and remember. So we have here a relationship, the ratio of the heat capacity, the specific heat capacity with a constant pressure, to the heat capacity of constant volume can be represented by this symbol. This symbol, how do you read this symbol? Gamma. Alright? Alright, next, we have to remember that for any processes involving an ideal gas, so we have some important formulas that we need to remember and understand how to use them and when to use them. So here's the formulas. We have Vv equals N times R times T. We have PA VA over TA equals PV VB divided by TB. and delta Q equals delta U plus delta W, and the other one is delta U equals N CV delta T. Okay, so we have to remember these formulas, and we should know when to use them and how to use them. Okay, so let us apply this into this problem. A 2-liter sample of oxygen gas has an initial temperature and pressure of 200 Kelvin and 1 atmosphere ATM. The gas undergoes 4 processes. 1, we have AB, from point A to point B, heated at constant volume to 400 Kelvin. Then from point B to point C, heated at constant pressure to 800 Kelvin. And from point C to point D, cooled at constant volume V back to 1 atmosphere. And from point D to point A, cooled at constant P or constant pressure back to 200 Kelvin. Okay, so here's the illustration or the PV diagram for the said problem. Now the question is, how many moles of oxygen or 2 parts of oxygen are present? Okay, so consider point A. So we have here the point A. So point A is considered to be here. Okay, so from our formula, we have the product of the pressure and the volume, or we have PV, P times V equals the product of the number of moles N times R times T. Okay, so that's the formula. Now, since you are asked to determine the number of moles of oxygen, so from this formula we can calculate N, right? So divide both sides by R times T. So we have this formula, N equal to PV divided by RT. And then substituting the givens, we have the pressure, that is 1 atmosphere. So 1 atmosphere is equivalent to 101,300 pascals. Alright? And volume is 0.02 meter cube divided by R, that is 8.31 or 314 joules per mole Kelvin, times the temperature of 200 degree Kelvin. So this is the temperature at this point, at point A. This is 200. And the value for R for this oxygen is 8.314 joules per mole degree Kelvin. Alright, so substituting the givens, we got here 0.0122 mole. Alright, so we got the number of mole from this. Please take note that the ideal gas law, that is PV equal to nRT, where N is the number of moles, the R is the universal gas constant. So in this formula, when you solve for n, no, from this ideal gas law, n equal to PV over RT, so the volume must be expressed in terms of cubic meter. And from conversion, 1 liter is equivalent to 0.001 cubic meter. Thus, for 2 liters, we have 0.002 cubic meter. And the value of R depends on the units involved, but it is usually stated with SI units as R equal to 8.314 joules per mole degree Kelvin. Okay? So you have to remember that statement. So you can see the summary of what I was saying. So from this statement. Okay, so remember that that's very, very important. Alright? Calculation. Now we have what we call process from point A to point B. We call it isochoric process. Remember, what's the restriction when the process is isochoric? So we have the volume constant, right? So the volume is constant, and the change of work is equal to 0. So when the volume is constant, so we can say that the change of volume is equal to 0. Okay, so now the question is, what is the pressure at point B? So pressure at point B. So to solve for the pressure at point B, then we'll use this relationship. The ratio of the pressure at point A to the temperature at that point equal to the pressure at point B with the temperature at that point B. So from here, so substituting the given, we have the pressure at point A, that is 1 atmosphere, and the temperature at that point A is 200 degree Kelvin, equal to pressure at point B divided by the temperature at point B, which is 400 degree Kelvin. Now solving for PV, we got PV equal to 2 atmosphere, or 1 atmosphere is equal to 101,300. So multiply that by 2, so we got around 203,000 pascals, or 203 kilopascal. Alright, is that clear? Any question? Now let's take a look again, the process from point A to point B. So delta Q equal to delta U plus delta W. So let's analyze first law for isochoric process from point A to point B. So looking again at the diagram, PV diagram. So from point A to point B, so there's no work done. So that's why we have delta W equal to 0, or the fact that this is an isochoric process, so the change of work is 0, or there's no work done in this process. So delta W equal to 0. So therefore, from the above relationship, delta Q equal to delta U plus delta W, so we can say that the delta Q is equal to delta U. And we know that delta U, which is the change of internal energy, is equal to the product of the number of moles times the specific heat capacity at constant volume times delta T. So substituting the calculated result and also the givens. We have for CV, the specific heat capacity of a certain element, that is oxygen, that is 21.1 joules per mole degree Kelvin, multiplied by the calculated number of moles, which is 0.122 mole. Then change of the temperature, that is the difference between the temperature at point B, which is 400 Kelvin, and the temperature at point A, which is 200 degree Kelvin. Or we have the delta U equal to 514 joules. Alright, so we know that delta U, which is equal to delta Q, that is positive 514 joules. So here, for this process, isochoric process, we have delta W equal to 0. Alright, any question? Now let's continue to the next process, that is from point B to point C. So we can see from our illustration that the pressure is constant from point B to point C. So now the question is, what is the volume at point C and point D? Alright? So from the relationship, now when we have the process that is isobaric, it means that the pressure is constant. So the change of pressure is equal to 0, or delta P is equal to 0. So therefore we can use this relationship that the volume at point B in this diagram to the temperature at point B equal to the volume at point C to the temperature at point C. Or we have VB divided by TV is equal to VC divided by TC. So what is the volume at point C and point D? So using this relationship and using the given items, so we have from this diagram that at point B the volume is equal to 2 liter. So as you can see here, so at this point, this is point B, which is same at point A. So the volume here is equal to 2 liter. Alright, so substitute this value in our formula. So we have here 2 liter for the volume divided by the temperature at B. So the temperature at B, that is 400. Alright, 400, so 400 degree Kelvin equals VC. So we don't know the volume here at VC, so we need to calculate that one. Alright, but we know the temperature at this point, that is 800 degree Kelvin. So divided by 800 degree Kelvin. Alright, so now we have VC, that is what is we are looking for. Now mathematically, we can get this by manipulating this equation, and we get VC, which is equivalent to the volume at point D, which is equivalent to 4 liter. Alright, so we got the volume at point C equal to the volume at point D, and that is equivalent to 4 liter. Okay, so hope you find that easy how to calculate those volumes. Next, let's find the change of internal energy for the process BC from point B to C. Okay, so process BC is isobaric. It means that the pressure is constant. So isobaric, so delta P is equal to 0. Okay, so for isobaric process, the change of pressure is equal to 0. So we have this relationship that in isobaric process, since the pressure is constant, therefore we have the change of internal energy delta U is just equivalent to the product of the number of moles times the specific heat capacity at constant volume and the change of temperature, or we have NCV delta T. Alright, so now substituting the given and the calculated value, so we have delta U equal to 0.122 mole multiplied by the specific heat of oxygen, that is 21.1 joules per mole degree Kelvin, multiplied by the difference, the change of temperature delta T, that is the difference between the temperature at point C and point B. So this is process BC. So temperature, the final temperature at point C minus the initial temperature at point B, that is 400. So therefore 800 Kelvin minus 400 Kelvin. So we got delta U, which is equal to 1028 joules, and that is positive. Okay? So now work depends on change in the volume. So work depends on the change in volume. Now let's find the work on this process, isobaric process. So finding the delta W for process BC. Work depends on change in the volume. Alright, so from this illustration, once again, so we have from our definition or from our previous studies in the calculus, we can find the work as the area under the curve. So in this case, we have a figure. This is a rectangular figure. So the work is simply the area of this rectangle. Alright, so again for this process, the BC, process BC, or the isobaric process from point B to point C, the pressure is constant, so delta P is equal to 0. So work, again from our calculus, we have the work is just the product of the pressure. The pressure, this is the magnitude of the pressure, and the change of the volume. So what is the volume from this point to that point, or from this point to that point? So change of the volume. So therefore change of work, or delta W, is equal to 2 atmospheric, or atmosphere for the pressure. So from here to there, that is 2 atmosphere. This is 2 atmosphere, that is the pressure, and the difference of the volume. So from this point, this is 4 liter, and then this is 2 liter. So from here to there, that is 4 liter. From here to there, that is 2 liter. So 4 minus 2, that is 2 liters. So 2 times 2, so we have 4 atm L, or the product of atmosphere and volume, which is in liter, that is equal to joule. So therefore the change of work is just equivalent to 405 joules. Okay, hope you got it. So as you can see here, our delta W is positive, that is positive 400 joules. Next, we'll find the change of heat for the process BC, or finding delta Q for the process BC. So first, let's analyze the law for BC. Right, so from the illustration, so again, let's focus on the point B to point C. So from our formula, that the change of heat equal to the change of internal energy plus the change of work, or delta Q equal to delta U plus delta W. So substituting the result, we have 1028 for delta U, as we have previously calculated, plus the change of work, that is delta W, equal to 405 joules. So therefore we have the change of heat, that is 1433 joules, or delta Q. So notice that our delta Q is positive. Okay, so just recall why it's positive. So I hope you still remember in our what we have discussed in our previous lecture. So we have here the delta U, that is 1028 joules. Alright, and we have the delta W, that is 405 joules. So therefore, summing up, we have delta Q equal to positive 1433 joules. Okay? Next, let's consider again the isochoric process, and this time from point C to point D. Again, we'll use the same diagram, the PV diagram. So the question now is, what is the temperature at point D? What is the temperature at this point here? Okay, so we will use the same relationship. Our original formula, we have the product of the pressure and the volume divided by the temperature at that point equal to the product of the pressure and the volume divided by the temperature at that point. So in this case, we are considering the product of the pressure and the volume at point C with respect to its temperature at this point C, equal to the product of the volume, the pressure and the volume at this point D with respect to the temperature at this point. So therefore, since the volume at C equal to the volume at D, therefore we can reduce the equation into this relationship. The pressure at point C divided by the temperature at that point C equal to the pressure at point D divided by the temperature at point D. So now we are looking for the temperature at point D. Then this, we have this temperature, right, at point C. The pressure, which is 2 atmospheric pressure. This is the temperature, 800. This is what we are looking for. This is the pressure at this point D, which is 1 atmosphere, and this is the temperature that we're looking for at this point D. Okay, so from there, substituting the given, right? So pressure at C, okay, so pressure at this point the same as at point B, which is 2 atmosphere. So we have 2 atmosphere here, and then temperature at C, which is 800, so we have 800, then equal to the pressure at D. So the pressure at D is the same as pressure at A, alright, which is 1 atmosphere. So we have 1 atmosphere here, then the unknown, which is the temperature at this point at point D. So again, solving for TD, or temperature at point D, then we have TD is equal to 400 degree Kelvin. Okay, so that's for the isochoric process from point C to point D. Okay, now for the process CD, so again this is isochoric process because the volume is constant, Okay, so from C to D, this is isochoric because the volume is constant at this point, that is 4 liters. So first we analyze the first law for isochoric process CD. Okay, so we know that for isochoric process, there is no work done. Thus, the delta W is equal to 0. And we have the relationship that delta Q is equal to delta U plus delta W. So therefore, our relationship, our equation turns into delta Q equal to delta U. But we know that delta U is just the product of the number of moles and the specific heat with a constant volume multiplied by the change of temperature from point C to point D. As point D as the final point, C is the initial point. Alright, so substituting the given or the calculated result, so we have delta U is equal to 0.12. Okay, so this is our N, 0.122 mole multiplied by the specific heat of oxygen, that is 21.1 joule per mole degree Kelvin, multiplied by the change of temperature. So our final temperature is 400 degree Kelvin at point D. Initial temperature is at point C, that is 800. So therefore we got the difference that is negative. Okay, so our result for delta U, so therefore is negative 1028 joules. Okay, any question? So delta Q, therefore, since delta U is equal to delta Q, so the change of heat is also negative 1028 joules. So delta W for isochoric process is equal to 0. Alright, next let us consider the process from point D to point A. Okay, so this time we will find the change of internal energy for the process dA. So process dA is isobaric because this is constant, no? From point D to point A, this is constant pressure, right? From D to A. So this is isobaric process. So for isobaric process, delta P is equal to 0. So from the relationship that delta U is equal to the product of the number of moles times the specific heat at the constant volume times delta T. Okay, so we can also have delta U equal to NCP. No, so we can take this formula for constant pressure as well. So we can have NCP delta T. So substituting, we have delta U equal to 0.122 mole times 21.1 joules per mole degree Kelvin times the difference. Okay, so this is the initial temperature here at D, then the final temperature at point A. So therefore we have 200, which is the temperature at A, minus 400, the temperature at D. So again, this part here is negative, so therefore we get the change of internal energy that is negative, and that is 514 joules negative. Now next we have to find the change of work, no, for the process dA. So for the process dA, we know that work depends on the change in volume, right? So here the volume change from point D, the volume here is 4 liter, then at point A, the volume here is 2 liter. So we know that work depends on the change in volume. So from this relationship, work is equal to the product of the pressure multiplied by the change of volume. So we know that at this point the pressure is 1 atmosphere, okay, and the difference between 4 liters and 2 liters, that is 2. So substituting this into this formula, so we get 1 atmosphere for the pressure multiplied by the difference, that is 2. This is the final volume, initial volume. So 2 minus 4 L, we have negative. So the unit is negative 2 atm L, or this is negative 203 joules. Okay? So next, let's find the delta Q for the process dA. Okay, using the same diagram. So analyze first the law for dA. Right, so from our relationship that delta Q equal to delta U plus delta W. So delta Q, we have calculated the delta U, that is 514 joules negative, plus delta W, that is also negative. So therefore we have delta Q equal to negative 717 joules, and we can check that one, no, from our previous result. We have here delta U, that is negative 514 joules, and delta W, that is negative 203 joules. So if you add these two negative numbers, so it will come up to be negative 717 joules. Okay, so that's the result, no, for this process dA, which is isobaric process. We got the change of heat equal to the sum of the internal change of the internal energy and the change of work, which is equivalent to the negative 717 joules. Okay, so this is the summary now for all processes. So we have delta Q equal to delta U plus delta W. So for all processes we use this relationship. So here's the summary. So process, we have AB, BC, CD, and DA, and we have the total, and that is for our first column. For the second column, we have there the delta Q. Okay, so this is the first column, this is the second column, third column, fourth column. So for delta Q, we had calculated that the delta Q, the change of heat for the process EB, which is the isochoric process, equal to 514. Okay, and then the delta U, that is 514, and there's no change of work because this is a isochoric process, so there's no work done. So delta W is equal to 0. Now for the process BC, we got the delta Q equal to 1433 joules, and the delta U was calculated as 1028 joules, and there's a change of there's a work done, that is 405 joules positive. No, BC is the isobaric process, constant pressure. For CD, from point C to D, that is the isochoric process, and we got the negative of 1028 joules, and that is for change of heat. The change of internal energy, that is minus 28 joules, and since this is isochoric process, so there's no work done, so that's why we have delta W equal to 0. Now for dA, so we got delta Q as negative 717 joules, and delta U was negative 514 joules, and since this is there's a change in volume, so we got a work done here, but this is negative. Okay, negative 203 joules. In terms of total, so delta Q total for the whole process is 202 joules, and there was no change of internal energy. And for the work, we have 202 joules. Okay, so that's for the summary.